Okay, so this is the BioSci 140 human physiology video for the introduction and data for Lab 27 renal function, which is basically looking at urinalysis. So the correlates to FOX for this lab are quite a few actually. 9.1, which is renal regulation, 9.2, which covers calculations and concepts for something called clearance, and 9.3 of FOX, which is the clinical examination of urine, which is looking at a urinalysis. So we're going to cover all three of these. So even though it's one lab, it actually has three different parts to FOX with it. When you handle urine, urine is considered one of those items that since it's a bodily fluid, that is contaminated. So we'll use the universal precautions, assume that all material is hazardous. You should handle your own urine, and if you handle somebody else's for some reason, you would wear gloves. Urine could be rinsed down the sink, however we like to dispose of it in the restroom along with the containers. Soft contaminated material would go in the biohazard bag, right, in the softs section. That would include things like pH paper that was used to determine the pH of urine. Reusable contaminated equipment would be washed with Anfill and then rinsed. That would include things like test tubes and slides for this. Obviously, as usual, no eating or drinking in the lab, even water, and then step out in the hallway if you need to and make sure you wash your hands, especially when you come back in. So for 9.1, we look at the renal regulation of fluid and electrolyte balance. Basically, everyone would pee in a cup. We would measure a number of different things from that urine. One of the things that we'd do is we'd measure volume. The cups have gradations on it, so you can't really see in this picture too easily, but if you look up here with the person wearing gloves, right, holding urine, you can see there's etching on it, and that's the urine volume, so you could read off the cup fairly easily. If you really wanted an accurate count, you could pour the urine into a graduated cylinder for a more accurate measurement. We would measure pH. That's not shown here, but we'll just use a pH strip. So basically, you dip the pH paper into the urine and pull it out and then compare it to a color strip. And that color strip would tell you the pH of the urine based on the color matching. One of the more interesting things to measure in some ways is the specific gravity. A specific gravity is measured with a device called a refractometer. And basically it relies on the refraction of light. So that makes sense when talking about the refractometer. And here's one shown up here in the top portion of this. And what you would do is you would load the urine right here on this sample, gently close the lid, and then hold it up to the light. And what the refractometer does is it basically measures the density of whatever object or fluid you have on the lens, in this case urine, over the density of pure water. By definition, the density of pure water would be given a specific gravity of 1.0000. So when you do that, because urine has dissolved particles that are basically things that have a greater specific gravity than 1, generally speaking, your urine specific gravity, because it's mostly water and some of those things, will have a specific gravity of usually about 1.003. That would be some very dilute urine, and up to about 1.040. One of the things you can kind of get a gauge of is what's the specific gravity of your urine based on its color. You can't be exactly too sure about it because there's factors that affect color. But just again, looking up here at this person's urine, the color's not too deep yellow, but the urine does not look much like water. So it's probably have a specific gravity about 1.020 when you looked at it. So once you're done with that, you would clean it with Kim wipes, and the Kim wipes would go in the biohazard because then they'd have urine on them. The other thing we need to do in 9.1 would be a chloride concentration. Remember that when you have a value in brackets, right, that would be a concentration of, and then chloride in the back brackets would be concentration of chloride. So in order to do this, you would take 10 drops of urine, so you get a little dropper and put them in a test tube. So here's like a test tube up here. And then you would put in 1 drop of potassium chromate. Potassium chromate looks like urine. It's this yellow substance that you just put 1 drop of that in. And then based on the concentration of the urine and the potassium chromate, of the potassium chromate and the silver nitrate, which is usually 2.9%, you would add silver nitrate and titrate it in. And what you would do is, since you started with this solution that was urine and something that looked like urine, it's this nice yellow urine looking solution. But as you add the silver nitrate, eventually it turns into this darker, cloudy, sometimes rusty, but this dark. Sometimes it's dark brown or beige or rusty color. But you're looking for some sort of change. And what you do is you count the number of drops of silver nitrate until this changes. And sometimes it flashes and goes back, so you have to mix it or shake it or at least swirl it and just keep on counting. Now, when you count the number of drops for that rusty color to appear and then not disappear, you're going to multiply that by one of these numbers. And what these numbers really reflect are the different concentrations of the potassium chromate and silver nitrate you could have. So it depends on what we have in lab that day as to whether you go times 68, 61, or 66. And to be honest, it really has very little difference between them because you're not going to have that many drops of the silver nitrate to change the color. So especially between the 66 and 68, the percentage difference is just so small it really doesn't matter too much. So that's what we would measure 9.1. Very quick, easy analysis of some of the different things. So what do we expect? Well, the urine volume depends on something called the void interval time, right? And if someone went to the bathroom, 30 minutes ago versus 7 hours ago, it's going to make a big difference in terms of the volume, right? So the longer it's been since you last emptied your bladder, the greater volume you'll typically have. Also, activity level and intake of especially water would all have an influence on it. So one of the things we like to know is what's called the void interval time. And so we would need the volume. We'd also need to know how long it was since you emptied your bladder previously. Okay. So the container, and again, we have different containers. This is actually a pretty small one in this picture, but containers typically hold 20 to 200 mils. So we get some sort of volume. We measure the pH. We expect urine pH to be about 6.0. That's average. Okay. Normal range is 5 to 8. So if your pH for your urine was between 5 and 8, it reflects a normal pH. If your pH is too low or too high, that is abnormal, and actually, in either case, increases your risk for kidney stones, as an example. Specific gravity, as I mentioned before, we expect it to be somewhat above water. In people that have very dilute urine, and so literally their urine would look almost like water, the specific gravity would be 1.003. And if it was pretty concentrated, most people don't go above about 1.040. Specific gravity, since you divided the density of urine divided by the density of pure water would be a unitless value. And for chloride concentration, you get a wide range of chloride drops to change the yellow to that rusty color I mentioned in the previous slide. And the reason why has to do with so many different factors physiologically about what control chloride concentration. Sometimes, chloride is controlled independently, and sometimes it's controlled with other ions that you may be exchanging chloride with in order to balance your charge. There's something in your body called the isoelectric equilibrium. Basically, it's the concept that your body needs to balance charge. You just couldn't continuously pee out positive charges because you would eventually have too many negative charges. So in order to balance charge, sometimes we will release chloride or save chloride with a positive cation, right, in order to balance that charge. In addition, the amount of chloride that you have in your body depends on a number of factors, not the least of which is dietary. So, students can sometimes freak out because we could have one student in lab that literally has 1 drop where it changes and somebody else has 32 drops. And both are normal. It's a huge range that's normal. So we're not going to worry about chloride too much, to be honest, but that's part of the reason why. And the physiological control of it gets pretty complicated. The other thing we're going to do, which actually on the top should say 9.3, is looking at the clinical examination of urine. All right, so 9.1, it's at 9.3 up here, see at the very top, but this one no. Basically, what we're going to do then is we're going to take that little cup of urine that you have, and we're going to take a chem strip. And chem strips look like here on the bottom, and they typically come in different ones. And you can get ones that are just for one thing, like as an example, one of the common ones would be like a glucose strip, or just had it for glucose, one thing. Or you could get it that had multiple ones, and they have what they call chem strips, 7s, 8s, 9s, 10s, 11s, 12s, 13s I've even seen. And what it basically does is it measures different things on the strip. So if you had like a chem strip 10, it would measure 10 different things directly on the strip. Some of the things in class of the strips that we have, we would not be that concerned with and wouldn't really care too much about the measurement, while other things that we would look at would be strips that would have the things that we were interested in. And sometimes the strips have things we can measure other ways. Like we would measure the pH with the pH strip. We measure the specific gravity with the refractometer, as I showed you previously in 9.1. However, the strips typically have a specific gravity and a pH measurement on it as well. But the clinical examination of urine that we would be most concerned about would be the things that are mentioned in FOX. And that would be whether there was protein, glucose, ketones, blood or hemoglobin, or bilirubin within the urine. Oftentimes, these also have other things like glucosides if you're looking for infection, and a few other things, nitrites and stuff like that. But we would only worry about these 5. So, when you use a strip in lab, what you do is you hold on to this end. See all the left in the picture has the different pads. Those have basically enzymes on them that will react with whatever thing it's going to test. And then you hold it just like it is, where down here at the bottom of the bottle, so the cap's up here, right? You would hold the strip and you would line the color up, and based on the color, it's hard to see in this picture, but you can see right here underneath each little color, there's a little number or a positive or a negative sign to show, oh, there's something here, or there's a, like down here, there's a bunch. And basically, if you look this outlined area right here, that's kind of like the normal section. And certainly while we have, a fairly large normal range sometimes, as an example, normal pH is 5 to 8, and these probably go in half pH increments. But you get the idea of how to measure that from those. Okay. The last thing they ask you to do in 9.3 is look at something called urine sediments. And in lab, we would just typically have, everybody could do it if they wanted, but we would look at least one per group. And somebody, usually the first one done, would make a slide of their urine. And basically, in order to do that, you fill the plastic tube about half full, you centrifuge it for a couple minutes, and then you pour it into the sink. And this part always kind of freaks out students because you're just taking the urine sample and dumping it into the sink. And what happens is, because the centrifuge tube is conical in shape and it narrows down at the bottom, it holds some urine there. And then you add a drop of what's called SETI stain. SETI is stored for sediment. It's this dark purple stain. You mix it by what they call aspiration. So you suck it up with a pipette and then spit it back in, and do that a couple times. And when you've mixed it fairly well, you add it to the slide. And then in Fox 9.3, on page 354 to 356, there are actually literally pictures of what urine would look like with different types of sediments in it. And students are sometimes disappointed, which is somewhat ironic, that they don't see much. I mean, we sometimes see crystals, we sometimes see bacteria, especially for women. We see occasional other things, but there's not much in it. And the good news is unexciting urine is a good thing physiologically, right? It means you're healthy. And like the book, if you look in Fox, has, as an example, a waxy cast from a diabetic rat. And students sometimes wonder, why don't I see that? Well, you're not a diabetic rat, so you're not going to see it probably, right? So that's the urine sediment, and we look at it under a microscope. Some of the sample data that is in the lab book, or I've taken from last semester actually, from some of the data we were able to collect, is, let's say that we had one person who actually knew when they went pee the last time. And when we do this in laboratory, I never ask the students to write down the exact time they went pee, because half of them don't remember, and it's just kind of, I don't know, strange. But a student knew in the one lab exactly when she went to the bathroom, and it was 30 minutes previous. And so we measured the volume of her urine, and it was 36 mils, and she did it in 30 minutes. So we can calculate what's called a urine production, or V, right? The urine production really is just saying how much urine do you make in a given amount of time. So that's pretty easy. You just take the volume, 36 mils, divided by the void interval time. That's the time you emptied the bladder, 30 minutes, right? And then empty it again, so that's 30 minutes. And go 36 divided by 30, which gives us a V, a urine production rate of 1.2 mils per minute. So pretty easy calculation. Typical pH, and depending on how well you can measure it, depends on what type of pH strips we have. Generally speaking, the ones we get are half pH increments, although in lab one, that one day we had some very good accurate pH strips, so we got it down to 6.1 pH. Remember, normal is 5 to 8, so that's a normal. Specific gravity is pretty normal. It's about 1.018, which means it's right in the middle of dilute, which is, again, 1.003, or really concentrated would be 1.040. So it's right smack in the middle of both of those, looking fairly normal. For the chloride concentration, the student got 6 drops. And that day, because of the different combination of potassium chromate and silver nitrate we had, you multiplied by 66. 6 times 66 is 366. milligrams of chloride per 100 mils per deciliter, basically, of solution. So that's, again, normal. We said anything between 1 and 40 drops is normal. So that looks fine. In 9.2, we weren't going to collect the data. We're just going to use some data I had before. We're going to measure something called the BUN clearance. BUN stands for blood urea nitrogen. So that's BUN. And we'll talk about clearance in the discussion portion of this laboratory. But clearance really is looking at whether or not we remove a substance from the body. And there's not a whole lot of ways to do that, but one is filtration and then just basically pee it out in urine. So we'll come back to that idea, but there's certain things we need, and one of the things we need to calculate the BUN clearance is the urine production rate. We just calculated that at 1.2 mils per minute. All right, so we just did that. The other thing we're going to need is to know the concentrations of BUN, blood urea nitrogen, in both the urine and the plasma. So what we could do is we could just use Beer's law, like we did way back in lab 2, and use Beer's law. For Beer's law, we need to know the concentration of the standard. So for BUN, you can buy that easily from a biological supply company at 50 milligrams per deciliter. It's the one we had. And then you put that with the reagent. You have a reaction, a timed reaction. You let it go. You measure the absorbance. So the absorbance of the standard was 0.04. Right? And then we do the exact same thing with samples from the plasma and the urine and measure the absorbance. And from these two values and the absorbance value we get from the spectrophotometer for the plasma and the urine, we can calculate the concentration. So as an example, the urine absorbance was 0.66 for BUN. And that meant the urine concentration would be 825 milligrams per deciliter. Using Beer's law, right, the concentration of an unknown equals the concentration of a standard times the absorbance of the unknown divided by the absorbance of the standard. So we can go back and replace the values we kind of looked at a few minutes ago. The concentration of urine, right, is equal to the concentration of the standard. We said that was 50 milligrams per deciliter, times the absorbance of the unknown, that's the absorbance of the urine, right, 0.66, divided by 0.04, right? So going back again, here's our absorbance and our standard concentration. So we just replace those, and you punch that in the calculator, you get 825 milligrams per deciliter. So that's the concentration of urine. We do the exact same calculation with the plasma concentration, except the unknown this time would be the concentration from plasma. Now, if you look at the plasma concentration, the plasma absorbance was 0.01. And if you put 0.01 over 0.04, that gives me 0.25, right? And 0.25 of 50 is 12.5 milligrams per deciliter. So one of the questions people sometimes ask, students ask, is, okay, why is the plasma concentration 12.5, yet the urine concentration is 825? The reason is we filter blood into our kidney and then we reabsorb the vast majority of the plasma. And since we're reabsorbing the vast majority of plasma and not necessarily reabsorbing as much of the BUN, then we're going to have a much higher concentrated. And in general, things in urine tend to be 40, 50, 60, 70 times more concentrated in urine than they are in plasma typically. So that's something we typically see anyway. So in order to then calculate the actual clearance, then we have these values that we mentioned. We have the urine concentration, that was 825 milligrams per deciliter. We have the urine production rate, 1.2 mils per minute. And we have the plasma concentration at 12.5 milligrams per deciliter. So we have those values. And we can use those values then to calculate clearance, which we'll talk about later, but clearance calculation is the urine concentration times the urine production rate divided by the plasma, and that's what you get in terms of that. So I just remember it as a simple little UV over P. So U times V divided by P, or urine concentration times urine production rate divided by plasma. If you're looking at those things, and again, we'll do these much more detailed in discussion, the plasma concentration, urine concentration would basically, their units would cancel, and you'd be left with the urine production rate type units of mils per minute. So you're going to see clearance is going to give values of mils per minute. Some other sample data, just look at it really quickly, is we measured the protein, the glucose, the ketones, the hemoglobin. Remember, HB, capital H, small b is hemoglobin, and the bilirubin in this person's urine. And everything came out negative. And we'd actually expect that. We expect that there's no protein in the urine, no glucose in the urine, no ketones in the urine, or very little, no hemoglobin in the urine, and no bilirubin in the urine typically. There could be very benign reasons why you might have some of these things, or certainly things that aren't of great concern in your urine, and that could be relatively normal, or these could be in your urine because there's some sort of pathology, and it could be a more serious pathology potentially, depending on what it is. So typically, though, we expect these to be negative, meaning there's none in it, which is good, right? Or really low. So sometimes it's like trace amounts are okay for certain things. So we'll pick up the next video with renal function discussion, Lab 27 discussion.